Hello, everyone. This is Wes Brewer. I'm with Oak Ridge National Laboratory. I'd like to share some work that we recently presented at the AI for Science workshop at SC23. This is work titled Entropy-driven optimal subsampling of fluid dynamics for developing machine learned surrogates. And there's an associated paper with this presentation. This is work that was performed in collaboration with a number of my colleagues at Oak Ridge National Laboratory, with Daniel Martinez at the Science and Technology Corporation at NASA Ames, and along with several of my collaborators at Mississippi State University. So over the past few years, I've been working on developing machine learned surrogate models. This started with initially with developing machine learned models for replacing physical sensors on helicopters. So our initial work in this space was developing a machine learned surrogate model to replace an accelerometer for an oil cooler for a Black Hawk helicopter. This work was published in 2018 and also in 2020 in the Journal of Parallel and Distributed Computing. Then more recently, we've developed a machine learned model to replace a cruise guide indicator. That's a model that basically monitors structural loads on 23 different components of a Chinook helicopter, which you see here at the bottom left. We've also developed machine learned surrogates for fluid dynamics, especially for turbulence modeling, wall-bounded turbulence models, and other types of flow and aerodynamics. And most recently, we've been developing machine learned models for digital twins. So we're modeling supercomputers. And so for each of these different types of applications, they're all trained generally by collecting massive amounts of data and then subsampling those data sets. But how we deploy the models may be different. So these are standalone machine learned models, whereas these are deployed alongside a reduced order or a lower fidelity solvers. So for example, we train on DNS data and then we deploy with RANs alongside RAND simulations. For the digital twins, we have different types of models. So we have like a job scheduler that's seeing inputs into actually a power consumption model, which then feeds into a thermofluids model. But we may also be interacting with different AI/ML models. And so for each of these cases, you basically have a workflow that emerges that's the same kind of workflow. And so in general, you're running many simulations to actually generate data, although for the rotorcraft, we're using flight test data. And and then from this, we extract a subset of data to curate our training data set. And then we use that to train the neural network. We do some kind of neural architecture search here. Then we develop the model, and then we test the model using some model validation procedures. And then finally, we deploy the model. And in some cases, this is deployed in conjunction with with a reduced order or a lower fidelity simulation. And sometimes it's just a standalone model. So in each of these steps, actually, you have to determine there's a number of questions to answer here. So if you're running simulations, how many simulations do you need to run? What are the variation of input parameters that you need to run? For the curating your data set, you need to figure out what's the optimal set of features, what's the optimal subset of samples, and if you're doing some kind of non-dimensionalization, if you're doing neural architecture search, what kind of base neural network architecture you're going to use, CNN, LSTMs, multi-layer perceptrons, how many layers, etc. For model validation, you need to maybe do some kind of uncertainty quantification, and you also need to know something about, is the unseen data in your training distribution or out of distribution? You shouldn't expect that if it's out of distribution that your model is going to work very well. And finally, when you deploy the model, you need to consider maybe doing graph optimizations, deploying at reduced precision, whether you're going to do in-memory deployment or using inference servers like TensorFlow Serving, SmartSim, or other types of approaches. So for each of these, there's been a lot of work actually, like, for example, in neural architecture search, a number of frameworks have been developed. We've actually developed our own framework that was published in 2018 called DELEO, Deep Learning Evolutionary Optimization. It was later published in a journal in 2020, JPDC. For the model validation, in addition to DELEO, there's countless frameworks like Keras Tuner, Optuna, DeepHyper. There's a number of others. For model validation, there's a number of frameworks as well. We initially started using Monte Carlo Dropout, but we've moved more to using the prediction intervals. So this PI3N method by Xian Liu et al., who's also a collaborator on this project. And then for the model deployment, we've done a lot of studies. We published 5 papers on this topic, looking at how to optimally deploy these machine learned surrogates on HPC. And so we've been actually developing a benchmark. Our most recent version of this benchmark is called OSME, which stands for the Open Surrogate Model Inference Benchmark. And that's a benchmark that we hope to release with ML Commons as an official benchmark for ML Commons in the future. But what I found is if you a lot of this work that we did initially, we were doing a lot of things trial and error to try to answer many of these questions, which takes a significant amount of time. So that's why initially we developed our own hyperparameter tuning to speed up this whole process of, instead of doing things brute force and trial and error. But what I found is there's not really been much work that's been done in how you do this actual step, how you optimally or how you compute the optimal subset of training samples to curate your training data set. And so for this, to address this issue, we've developed something called DataSift-ML, which is an automated method for intelligent subsampling of larger data sets to curate training data. And that's what this presentation and our paper is about, some initial work in this space. And so just to give the general problem here is that simulation data sets can be extremely large. So for example, DNS data sets of stratified turbulence are 11 terabytes for one variable for one time step. More data is not always better. So the reason for this is data is often highly skewed. And so there's a nice paper by Nakiran et al. In 2019 that addresses this issue and shows they actually prove that how actually less data of the right data, the correct amount of data, can actually produce better models than using more data in general. We also ran into this in this paper that we recently put out with Matthew Boyer in 2020 on our development of a machine learned cruise guide indicator. Another problem here is that training set generation is traditionally a high labor intensive activity that relies on physical intuition. So that means if you're doing this, if you're curating your data set using trial and error, you generally need to be a subject matter expert in that area. This was something that came out of the Carabin and Perez paper in 2020. And so the question we're trying to address in this paper is, can we train better surrogate models faster by automating the curation of training data? So there's been a number of methods for reduced order modeling, and I'm not going to address every method here, but I'm going to cover the main ones. One is the simplest approach is random sampling, and actually is quite an effective approach. You can consider random weighted sampling or Latin hypercube sampling, among others. And then there's stratified sampling, where you do for some level of clustering, and then you may draw evenly from those clusters. Then importance sampling, so drawing samples according to their importance, such as gradient, variance, or in our case, entropy. There's projection-based methods, such as proper orthogonal decomposition, POD, or dynamic mode decomposition, DMD. And then there's neural network-based methods, such as using either autoencoders, active learning, or knowledge distillation. So our method basically is a combination of these first three approaches. And we actually considered experimenting more with projection-based methods, but didn't want to focus too much on that area. There's been a lot of work in that area, but also at the same time, these methods assume linear dynamics, which may not be appropriate for when you're doing things like turbulence modeling, which are highly nonlinear. And then neural network-based approaches. So considering methods like autoencoders and that, they may do very well at data reduction, but the issue there is sort of the interpretability or explainability of your downsampled training data. So our work is based on the principle of maximum entropy, which states that the probability distribution which best represents the current state of knowledge about a system is the one with largest entropy. And this goes back to Edwin Jane's seminal paper in 1957 on information theory and statistical mechanics. Most recently, the Carabin and Perez, who I mentioned before, have used this approach towards automated training set generation. They were, as far as I know, the first that used this method towards developing automated training set generation. And what they mention in their paper is two types of applications for maxent, and that is using maxent for simulation design, so to figure out sort of the optimal set of simulations that you want to run. And second is using maxent as a subsampling tool, where you're actually using the method to given a large raw data set, what's the optimal subset of that data set that can be used for training neural networks. And so our method in this this particular paper is focused on this second goal, using maxent as a subsampling tool. So this gives a high-level overview of the approach that we've developed. First, you run some simulations. In our case, we're using OpenFOAM. Then you do some kind of clustering analysis on some high-level descriptor variable. In our case, we're using k-means clustering, and we're using like pressure, vorticity, or velocity, something, one of those variables for our cluster analysis. And then you basically take your clusters and turn those into probability distributions. And then you can compute the relative entropy between those clusters. And that will give you a graph, which is step 4 here. And and in the graph, then now you can compute the relative, you perform graph analysis of the relative entropies in order to compute n-degree strengths. That's the if you sum all the weights that are coming into a node, and now these weights are actually relative entropies, so you sum all the relative entropies coming into a node, that gives n-degree strength, the n-degree strength of that node. And now we can down select the data by probabilistically selecting samples proportional to the n-degree strengths. So I'm going to go through in the next 5 slides each of these steps in more detail. So first we run simulations. And so since we were initially wanting to develop a method, we simplified as much as possible the type of simulation we wanted to run, because we need to do a lot of iterations to experiment and with developing such a method. So we're using OpenFOAM to simulate 2D flow over a cylinder. In this case, we're running a low Reynolds number of 1,267. And we run this for 10,000 time steps, although we only write out every 100 time steps. And then we're solving the conservation of momentum and mass. And there's two types of neural networks we can think about in general, surrogate models producing here. One is what we call global quantity prediction. So for every time step, take a subsample of points and predict some single scalar value, such in this case was drag force. And a second type of problem is local field prediction. So predicting local field values at each grid cell, such as turbulent kinetic energy. In this case, for each of our subsamples, we want to predict some quantity. So in our initial version of this work, we're just focused on predicting global quantity prediction of drag force. And then we need to, step two is defining some high-level descriptors or cluster variables. So for Carabin and Perez's paper, they focused on applying this method to material science. So they were, their high-level descriptors were bispectrum components, for example, local density around an atom. Matthew Boyer and I and a few others applied this method towards on flight test data. So in that case, we didn't have, basically as a high-level descriptor, we just represented the signal in terms of the mean, the slope, the variance, and the curvilinear distance. So we took the signal, we broke it into windows based on time, and then we computed the mean, slope, variance, and curvilinear distance to sort of have a generic representation, high-level representation of the signal. And that actually worked pretty well for that type of data. In this work, based on fluid dynamics, and as far as we know, we're the first that has applied this to fluid dynamics, we're using quantities such as vorticity, which is a higher level descriptor of the flow field, pressure, velocity, or turbulent kinetic energy. Step three is to do some sort of clustering analysis. So we used k-means clustering initially. You could also use dbScan or self-organized maps. And so in this case, we want to, the k-means clustering partitions data into k number of clusters, where each data point belongs to the cluster with the nearest mean. And so generally you'd use some kind of elbow analysis to find the optimal set of clusters. We did that, and we found that the optimal set of clusters, according to the elbow analysis, was about 7, somewhere between 5 or 10. And but in reality, we found that actually using a K of much larger, such as 20, actually worked better with this type of method, because it gives you the categorized the dynamics in a more fine-grained manner. And so here shows some examples of k-means clustering using vorticity. So you can see how it nicely separates out the background flow field from the vortex street wake, and it categorizes the wake in terms of the sign of vorticity and things like that. We use this shows doing a cluster analysis using using pressure. And then this shows the cluster, the frequency, if we look at histograms of the individual clusters, and as compared with the data before it was clustered, you can see how the clusters break down in their ranges. And step 4 then is computing relative entropy between the clusters. And so to do this, we use Kullback-Leibler divergence. And so the KL divergence, which is defined here measures how one probability diverges from another, or more specifically, how much information is lost when Q is used to approximate P. So if we have our probability distributions from our the different clusters, then we can, as I mentioned before, we can then turn this into a directed graph where the weights of the graph are your relative entropies computed from D here. And then by doing that, you can come up with produce an adjacency matrix of relative entropies. So in this case, we have 20 clusters on our y-axis against the 20 clusters on the x-axis, and then you have the relative. It shows basically the relative entropy of each of these. And then so if we want to get the n-degree strengths, then we can just sum the rows of the adjacency matrix to get our n-degree strengths, and then from that shows us how we can then subsample that, which I'll show in the next step. But before that, I wanted to mention that how you can think of this, and this is really the heart of this approach, is that this is going to measure how two different clusters, how much they differ. And so if you would think of in this case where we have clustering, k-means clustering and vorticity, you can imagine how much like the green cluster here is going to differ from the background cluster, or how much the green is going to differ from the you could expect a smaller difference within this range versus the background range. And so you're hoping that the method won't select many points from the background, and you'll see that it selects very few from the background if you cluster on vorticity versus selecting points that are of interest. So now we go to our final step. In this case, we want to sample a subset of points that are proportional to the relative entropy and degree strength. So that means if a particular cluster has a high n-degree strength, then it should have a higher probability of being selected in your subset. If it has a low relative n-degree strength or relative entropy n-degree strength, it has a low probability of being selected. And so this is our original grid for our simulation. And we did our initial analysis on the original grid. And so you can see when we use vorticity and then subsampled points here, most of the subsamples are actually in the wake. We get these samples on the wall because of the boundary no slip boundary conditions. Then if we do the same kind of analysis using pressure, you get something that looks like this. So it's interesting, as I mentioned before, it hardly selects any points in the background flow field. And actually, when we did this analysis, we found that actually random sampling was actually working really well. I mean, on par with our method. But the reason for this is because of the grid refinement, the random sampling was clustering a bunch of points right around the center, which you can imagine actually would give you a very good is a good way of getting a good drag prediction. So to do a true comparison between our method and random sampling, we needed to produce pure random sampling, and in order to do that, we needed to work on a Cartesian-based mesh. So we we interpolated the flow field onto a Cartesian projected mesh so that each point has a equal probability of being selected in terms of random distribution. And so then we run our subsampling, maxent subsampling. In this case, we're using velocity. And then here you can see actually just using random subsampling. So we have pure random sampling here, and so we can do a more fair analysis, more fair comparison. So now in this slide, we show the results of the maxent approach versus random sampling. And so here you see the full data set as in the gray, and this is a histogram distribution. And then you see the random sampling. So random sampling is going to select the, as far as subsamples from, it's going to end up selecting more samples from areas that are more represented in the flow field, which is what you see here, whereas that the maxent tends to select samples, more samples that are, it selects a more diverse, creates a more diverse data set, and it selects samples that are more underrepresented in the flow field, which is what you see here. So you see that that maxent has a better coverage of selecting. It ends up boosting, basically boosting underrepresented samples in the flow field. And so then if we take this method and we use it to train a neural network, and so we run the subsampling and then we run a training, and then we do that whole process as a single event 5 times. Then we compute the test error each time. We compute an average and a standard deviation, and then to come up with this plot. And what this plot shows is that the subset of the subset size relative to the entire data set. So this is so in this case, we're subsampling 140 points from a total of 10,800 points, or 10,800 samples. So our subsampled representation is 5% of the total the full data set. And then we do this for 5, 10, and 20%. And then we compare this between maxent and random sampling. And so you can see that consistently maxent produces lower test error this is on unseen held out test set. And generally it produces more reproducible results as represented by the standard deviation. And so some closing thoughts. So we introduced a method for optimal subsampling based on the principle of maximum entropy. This method produces more deterministic and reproducible machine learned surrogate models than random subsampling. It significantly speeds up the data curation process and training for fast prototyping. And this code actually, which we call DataSiftML, is freely available at this link here, which is github.com/ATAIMS/DataSiftML as one word. And finally, as far as future work, we're currently actually working on applying DataSiftML to large and complex LES and TNS simulations, magnetohydrodynamics flows, and stratified turbulence data sets. And so in general, we would like to use this method to study temporal forecasting. We already have that built in, but we just haven't done a lot of experiments with it to really study how it works for temporal forecasting. We would like to also extend this method to 3D to work with larger LES and DNS data sets, and we'd like to also parallelize the approach because it's becoming computationally expensive, especially working on these very large data sets. And here are a number of our references that I cited during the presentation. So thank you for taking time to watch this video. There is a paper under the same title that's available. And please feel free to reach out if you have any questions how to use this method. We'd love to collaborate with you. Thank you.